Okay, so far we've defined what an acid is and we've defined what a base is, but what happens when you mix the two together? Well, that's called a neutralization reaction. So an acid and base, they have the effect of canceling each other out. So if you have something that's acidic and you want to neutralize it, you can add a base. And if you have something that's basic and you want to neutralize it, you can add an acid. So here in this example, we have a substance that's in this flask, and what we are doing is we are neutralizing it. So I'm going to go ahead and pause this for a second. And so you can see that as the drops were coming out of this substance, the drops coming out were OHs, and the OHs, as they're going in, you can see, if you watch carefully, I'll play it again, you can see the OHs are combining with the hydrogens that are in the acids that's in the flask there. And as they're combining together, they are forming water. You can see the equation that we have down below. And of course, water is neither acidic nor basic. So this thing is becoming less and less acidic as we watch. So we keep going until there are no longer any H pluses left. At the point in time when there are no longer any H pluses left, then we know that we're neutralized, and we would have to stop adding the base. Now, if we kept going too far, then it would be basic. So we would need to know when to stop, and that can be a little bit tricky. But again, just to summarize what was happening here, the hydronium, the hydrogen ion from the acid, combines with that hydroxide from the base, and we get water resulting from these things here. So neutralization reactions, the goal is you've got to have equal amounts of both acids and bases. If you have equal amounts, then your final solution will no longer be acidic, nor will it be basic, and at that point we say that it's neutral. So there's lots of examples where we have to neutralize things. We talked about monitoring the pH of swimming pools. So if your swimming pool gets too acidic, you've got to go and you've got to add a base to your pool to bring it back more towards neutral. Maybe you spill a strong acid in lab. Baking soda is a base, so you can add that to help to neutralize that. You read an article on antacids, the stomach ulcers, so that's when your stomach gets too acidic. So you want to take some antacid tablets, which are bases, to help neutralize the highly acidic part of your stomach there to bring it back more to normal. So there's lots of examples in everyday life where we need to neutralize this. Now, of course, in order to neutralize it, there's a couple things we might want to know is, we want to know, how do we know when this thing is neutralized? Because acids look just like water, bases look just like water. When they've been neutralized, well, we're making water. So if we didn't do anything, we would never know when it's neutralized. Acids and bases, those reactions by themselves, they're not the most exciting reactions to watch because you've got water, it looks like water, you're making water, it doesn't really look like anything is happening. So one way that we can tell what's going on is by using an indicator. And we want an indicator to tell us when our solution has been neutralized. Now the point at where the solution has been neutralized is called the equivalence point. Very important terminology here. So we want to choose an indicator who is going to change colors when it's been neutralized, or in other words, to change colors at the equivalence point. Now, we talked about indicators earlier, and we know that indicators have a certain pH level where they will change, and so when an indicator changes, it's called the endpoint. So to find out what we know, we want to make sure that we choose an indicator whose endpoint is at the equivalence point. In other words, an indicator that will change colors when we have officially neutralized things. So we want to choose the proper indicator. So we've seen this chart of some common indicators before. We see they all change at different pH levels. For example, litmus paper, we've already talked about the fact that it has an endpoint at 7. So it is really good to know if something is an acid or a base, or if it's been neutralized or not. Other times you might want to know different pieces of information. Maybe you want to know if you have a strong base or not. So yes, in that case, the alizarin yellow would be a good choice because that's going to be red if it's a strong base. If it is yellow, it might be a weak base, it might be neutral, it might be an acid. So it's not very good to find out if I have an acid or a base, but it is good to find out if I have a strong base because I know if it turns that pink color, it's a strong base. If not, then I know it's not. So neutralizations, again, what they would look like. Neutralizations here. Here we have an acid. Again, it looks just like water. So we're going to put that in a flask. And so obviously to neutralize that acid, we are going to be adding a base to it. So in the other cylinder, there's our magnetic stirrer just to keep the solution stirred. So here's our base we're going to add. And of course that also looks just like water. We're making water. Is it neutralized yet? Is it neutralized yet? Well, I don't know. I don't know. So we keep adding more and more base. And hopefully you'll be able to see the color show up here a little bit. It's a little bit faint. There we go. You can see that we added an indicator here. And that indicator told us now that we know it's neutralized. So now we know when to stop adding. We know that it's neutralized, and we can then figure out what information we want to know from there. So in this case, as we already said, the indicator that they used was phenolphthalein, which is a common indicator for neutralizing. Now technically its endpoint is 8, so technically at that point in time the pH was 8, but remember if your pH is 8, you are pretty much neutral. Technically you're basic, but that's still barely basic, pretty neutral. So neutralizations, we said that it's not really a 6 type, it's actually one of our other types. So look here, here's our example of a neutralization reaction. Do you recognize that? Which of our 5 types is it? You guessed it, it's a double replacement reaction. So we really already know how to do neutralization reactions. All that's going to happen is the hydrogen from the acid is going to combine from the hydroxide from the base, and we're going to get water. And then we'll have the other 2 ions combine to make a salt. Remember, to the chemist, the word salt simply means any ionic compound. So in this case, our products will just be water, and in this case, our sodium sulfate is our salt. Here's another example. And again, we get water and our salt. So they're just simply double replacement reactions, no big deal. You already know how to write equations for neutralization reactions. Now the last thing I want to mention here is measuring the strength of acids and bases. Now we already know our definition of acids. It's the presence of that hydrogen ion, and so really it depends on what the concentration. The more concentrated that hydrogen ion is, the stronger the acid is. So the difference between a strong acid and a weak acid is that strong acids completely dissociate in water. Weak acids only partially dissociate. Now to explain what that means, here I have some HCl. Now maybe I have a bottle that says 1 molar HCl, which means I have 1 mole of HCl inside of that. Well, since it is a strong acid, I start with a whole mole of HCl, but all of it dissociates into my 2 ions here. So after it's all mixed in, really, since it's HCl, I actually don't have any HCl. It is all changed into those hydrogen ions and the chloride ions. So I have a whole mole of hydrogen ions floating around in my 1 molar HCl bottle, which is a lot. It's highly concentrated. And so, I'm not going to want to stick my finger in that. That's a strong acid. Now let's say that I had 1 molar acetic acid. That is a weak acid. That means it does dissociate. It does split up, and hopefully you recognize the 2 ions there, the hydrogen ion and the acetate ion, but only a small amount of it actually breaks apart. So if I started with a whole mole of the acetic acid, only a little bit of it dissolves. I might still have 0.9 moles of it that's left undissociated, and only a small amount, maybe only 0.1 moles, actually has changed into the hydrogen ions. So even though the bottle says 1 molar and 1 molar, they're very, very different, since one's a strong acid and has a whole lot of these hydrogen ions floating around in the bottle, and the other one's a weak acid and just a little bit of dissociated, so there's only a very small amount of those H+ ions. So you can't just go by what the bottle says. You have to know whether it's strong or weak, and you really need a measure of those hydrogen ions. So the higher those concentration of hydrogen ions, the stronger the acid will be. So do you remember our 3 acids on our 3 strong acids on our list of 7? It's nitric, hydrochloric, and sulfuric. So the way we come up with to actually measure the strength of the acid is by using the pH scale, which we're already pretty familiar with. It ranges from 1 to 14. Technically, you can approach 0. We hopefully already know that 7 is neutral. If you're lower than 7, then you're an acid. If you're higher than 7, then you're a base. And the farther you are away from 7, the stronger you are. 1 is the strongest acid. So the lower the pH, the stronger the acid. And, of course, the higher the pH, the stronger the base. Now, just a little bit of info about the pH scale. It's a little bit confusing. Why does it go from 1 to 14, and why is it backwards? Well, one thing is it's a measure of the concentration of hydrogen ions. And so you might think, well, wait, why is a pH of 1 the strong acid? Because pH of 1, well, 1's the lowest number, but that's the strongest acid. How can that be? Well, it's because of the way it's calculated. The pH is actually the negative log of the hydrogen ion concentration. The brackets there means concentration. So you might remember, maybe you don't remember from your math classes, logarithms. It's more than just a button on your calculator. What does that button do? Well, the log is simply what power of 10 your number is to. So, for example, let's say that my hydrogen ion concentration was 1 times 10 to the negative 7th. Well, the log of that number is what power of 10 it's to. Well, that's to the negative 7th power. So the log of that number would be negative 7, and the pH is the opposite of the log. So that means the pH would be 7. If my hydrogen ion concentration was 1 times 10 to the negative 3rd, well, the log, what power of 10 is that to? Is negative 3, and so my pH would be 3. Finally, if my hydrogen ion concentration was 1 times 10 to the negative 9th, the log of that would be negative 9, and the pH is 9. Now, of course, these are all nice, pretty numbers. It's not always this pretty. Sometimes you might have to use your calculator. And for this course, we're actually not really going to use that equation. We'll use that a lot in Chem 2, but we want to have some understanding of where that comes from. Now, those are kind of weird-looking numbers, and we still have to answer, well, why does the pH scale go backwards? Well, look at these 3 concentrations. Which one of these is the biggest number? And so, yes, 1 times 10 to the negative 3rd, that would be 0.001, whereas 1 times 10 to the negative 9th, we'd have 8 zeros. I don't know if I counted right or not there, but we can see that that is a much bigger number, and so that has a higher concentration of hydrogen ions. So the lower the pH, the stronger the acid, and that's why it works that way. So now you know what you need to know about acids and bases and neutralization reactions. So good luck, and happy working with acids and bases.